So for question number 2, we are given that there is an insulating ring with a total charge of positive Q, and that has a given radius r on the xy axis. And I've drawn that in the top left. You can see the x and the y axes and the ring of charge given radius r. And then we're also given that there is a point P on the z-axis at location 0, 0h. And so I drew that next to it. You can see the x-axis, and on the x-axis lies, you can see a side view of the ring of charge with radius r. And on the z-axis, the crossing axis, you can see point P at the top that I labeled, and you can see the distance h from point P to the ring of charge. And this picture is a little marked up. You can see I drew a triangle. And that's for a little bit later, but this is just the general idea of what's going on. So for part A, we are asked to derive the magnitude and direction of the electric field at point P. And so first off, all charges from the sides of the ring will cancel out, so it's essentially just going to be one charge from the center, is how it's going to work. And so I used a formula E equals kq over r squared, derived from Coulomb's law, which is the force equals k q1 q2 over r squared. And so I simplified that a little bit so I could solve for the electric field at the point P, and I call that E of h. So that equals kq cosine theta over r squared. And I used q cosine theta instead of q because we don't know the little r, and there you can see I have the theta there, and we're actually trying to use the vertical component that I drew going up to P from the ring. And so I used a little bit of trig, and I determined that would be kq cosine theta over r squared. And so since the cosine theta equals h over little r, or adjacent over hypotenuse, that simplifies further to kqh over r cubed. And so since I don't know little r, I don't know what that is, I thought I'd try to change it into constants that I do know, in this case h and capital R. And so I used the Pythagorean theorem and did r squared equals h squared plus capital R squared. And so that leads to little r being the square root of h squared plus capital R squared. And so I just plugged that into my equation, plugged that r into my equation. And so then I get the electric field equals kqh over the quantity of h squared plus capital R squared to the 3/2. And so to go back to answer the question with the direction of the electric field, since the electric field this helps that the electric field kind of cancels from all the sides, and that there is kind of one going up the center. And since there is a positive charge coming out of the ring, this kind of deflects the electric field to, kind of repels it away from point P, so it'd be going upwards. Alright, so for part B, we are asked to derive the magnitude of electric potential at point P. And so I used another formula for electric potential, V equals kq over r. And so then I decided to take the derivative of those to get dq, and so then dv equals k dq over r. And I guess since we don't know r, little r, I plugged in what I'd calculated before with the Pythagorean theorem. So that equals k dq over the square root of big R squared plus h squared. And so then I decided after that to take the integral of everything. And so the k over square root of r squared plus h squared, those are all constants, so they come out of the integral sign. So you have that times the integral of dq, And so we learned that dq equals lambda times dA. And so I simply plugged lambda times dA into dq, took the integral, and then I got k times 2 pi r, which is the area, or excuse me, the derivative of the area, so the circumference. So k times 2 pi r times lambda all over the square root of r squared plus h squared for the electric potential at point P.